record to cloud. And then we are going to, and so today, I'm going to go over our textbooks, major business, okay? And I finish my parts. And for the textbook, and also help us to review, okay, the set and the map, this chapter. And so the objective, we already learned everything. And if you wanted to double check, you can check, okay. And the motivation, it's regarding set, okay. The set, so set, we know the concept is unique, is it? No duplicate, is it? That's the major concept, no duplicate. No duplicates, okay. So that's the major concept about set. And then here, we also discuss this quite often, is it, regarding the collection. So basically now we learned majority of the collection framework, okay, the hierarchy. And regarding the collection, and the collection, it has another interface about iterable, okay. So we all know that. And the iterable is a functional interface, is it? So once again, we see the word functional, is it? So functional interface. And the functional interface is what? Only one, abstract method, okay. So keep all of those in mind. And that's why we have that lambda expression. Okay, and so that interface will give you that abstract as the iterator method, okay. And the iterator method returns what? It returns iterator. Iterator is what is also an interface, okay. So it's also an interface, but it has a couple of methods. Is it like next, has next, and remove, is it? And that's the general information about iterating. And the collection, that is, so why it's named as collection, now it makes a lot of sense. Is it because it stores more than one item, is it a group of items, okay? But based on how you place all of the items, is it? So that's why under the interface, generally speaking, we have queue, list, and set. These three you can clearly see, is it? They are at the same level, is it? And under queue, then you have deck, is it? And under set, we have sorted set and navigable set, is it? So those are regarding interface of the collection. Collection has a general, is it? So the major feature is it add, it support, add, remove, and contains, is it? Contains, is it? But based on each one of it, then it has each one of the interface, then they have added their own feature, is it? Added their own feature. Okay, and the abstract class, and we didn't see a lot, is it? And then we see a lot for all sorts of concrete class, priority queue, linked list, array list, stack, is it? And then we also learn hash set and linked hash set and tree set, is it? Tree set. Okay, and so set belongs to collection hierarchy. Keep this in mind. And then let's just do a quick review because we already discussed of this. Probably let me do this. Large more, okay. And we use these three a lot for set, is it? And who still remembers the major difference among these three different kind of set? So the major differences,
whether it is sorted or not.
Which one you said is disordered?
So hash set and linked hash set
Yeah,
is not sorted.
Yes, yes. So not sorted. Is it not sorted? And it's implemented based on what? Implemented based on the concept of hash table, is it? So it's using hashing concept, is it? And sorted is what? Is a tree set. Is it? This is sorted. So based on your needs, is it? And you can select either hash set or tree set. Okay.
Excuse me, what is the
Yes.
difference between linked hash set and hash set?
Oh, linked hash set. So hash set doesn't maintain insert order. Okay, and linked it keeps inserting order. So that's a major difference between these two, okay? But they all use hashing, okay? But for linked, it also linked as the order, is it? So when they internally, they also, it's a doubly linked list, okay? So they also maintain the order. So the first one you add to the set, it's going to be at the beginning. The second one is going to be at the second. The third one is going to be the third. Okay, and for this hash set, it's just no order. Is it? No order, just based internally. Okay, it's using hashing. Okay, so that's a major difference. And the tree set is arranged as a tree. Okay. Okay, so this is regarding set. Okay, regarding set, the hierarchy. Oh, sorry. How can I get? That's messed up. Hold on. Okay, let me. It's just a close the window. Okay, then let's move on to the next one. And I think I needed to. Okay, so it needed to. So anyway, so this is give us the general idea about the collection interface. Is it with collection interface? If you recall, the major is add, remove, and contains. Is it? And of course, it adds. It also has add all. Add all, then it's not a single item. It's another collection. So any collection will be allowed, and it contains all. It's also check another collection, okay? And remove all is also another collection, okay? And also later on we will learn in detail, okay, in another chapter about the hash code concept, okay? And the equal, and this two also kind of has a lot of association. And also the collection also has a method called toString. It can convert a collection to an array, okay? So this is just regarding collection interface, okay? And the set interface, and we already know, is it the major thing is no duplicate elements. Is it? And the duplicates based on what? Based on the equals. Okay, the equals is from So it's generic based on what you define that type. That if you don't override the equals, then it will use the objects classes default definition for the equal. So it's a reference, is it? Unless you specifically define the equals, then it checks for the deeper copy, is it? So this is a concept we already reinforced a lot of times in CS2, if you recall, is it? So anyway, so it depends on, so this equals is based on the type, okay, of the set. And this is general idea of a set hierarchy, is it? A set hierarchy, we know that it has, and then for the hash set, and the hash set, it allows multiple different ways you can create the concrete hash set, is it? And it allows some collection, initial capacity. And if you recall, like this has the initial capacity and the load factor, is it? And yesterday, I remember I also explained the concept behind this is once it reach the capacity, the initial capacity times the load factor. Load factor, is it? Then it's going to increase the capacity. Okay, increase the capacity. And after increase the capacity, then the hashing is also changed. So it involves rehashing. Okay, and what that means later on in our later chapter, you will see what does the hashing of that means. And for sorted interface, because it's sort, so it allows like first to last, is it head set, tail set of those. And for navigable, is it, then it also has more, it also allow you to remove first, to remove last, is it, and the lower, higher floor ceiling of those, okay. Okay, so it's just a different, more sets of operations going to be allowed. Okay, abstract set, and we used the major as for the hash set and the linked hash set. And the hash set, okay, so let's see. So it says a hash set also duplicate free, is it? So it's a concrete class. And for hash set, it needed to implement hash code. Okay, is that in some manner that probably disperse the hash code. Okay, so that's regarding whatever you're going to add to the set, the type, is it? It's a book, or employee, or string, or like integer, is it? So all of those internally, they should have the hash code method correctly defined. Okay, that's what this part means. So it needed to implement the hash code method properly. Okay, and later on we will learn that. The hash code. So anyway, so that's a hash set the concept, okay. And the hash set here, the textbook has an example. The hash set is filled with strings, okay. And it said it can use iterator to traverse the elements, okay. And we can take a look the example. And for the textbook, the slides, some slide, they have this green button, okay? And if you place the slides in the show mode, and you can view the code, okay? So let's take a look the example. So let me go to this and oh, then I needed to re-sharing, I believe. Okay, so, and if you click that green button on the slide, it will bring you to the textbook example, okay? For this example, it's just does some string type of hash set, okay? And the variable type is just use the set interface, and we know that's allowed. And this is concrete class, is it? So it will does the dynamic binding, is it? And then you just add each individual string, is it? And you just call the add method. And over here, and the slide said it use iterator, is it? And why it's allowed to do this for each loop? It's because the iterable interface. Is it? And the hash set anyway, it's in that hierarchy, is it? So that's why this is allowed, because internally that iterator already taken care of, is it? And what it does is it convert all of the string to uppercase, okay? That's what this example does. It's pretty straightforward. And over here, you can also call this for each method. It's also also allowed, okay? And what over here does, it's a lambda expression, is that? And we can further later on take a look what that for each method's argument. And for this example, and you can also in this it can also run and compile. And can you see my new a new page right now?
Yes.
Okay, okay, great. And so this online it's interactive, is it? It can also bring you to this new a new live running, is it? And you can also run. And if you run it, did you see? And it will it should give us and compile and run. Oh, okay. I run it. Yeah. Click the answer. Is it? And it will also give you the running result. Is it? And the running result, if you take a look, the set is not arranged as the inserting order. Is it? You insert London first, but over here, did you see San Francisco goes to the first of the hash set? That's why we say hash set doesn't maintain the insertion order, okay, insertion order. And then over here, what it does, okay, it does do the uppercase, is it? It convert every city to the uppercase. And then over here, it sets to lowercase, is it? So we saw just the lambda expression to do that. Okay, so that's this example. And then let me close this, move on to the next. Go back to our slides. Okay, that example is pretty straightforward, okay, compare with our example. And okay, we already learned that. What the next example shows is still a hash set with string, but this time it uses linked hash set, okay? And it also says use iterator to traverse, okay? So let's take a look at that example. And I think I needed to stop sharing and bring this new, this time, yeah. So this time is the linked hash set, as a linked hash. So we still fill in with those cities, is it? And we do the loop, okay, for each loop. And then let's see the running result. And we can compile and run, and we can take a look at the answer. If you take a look at the answer for linked hash set, this time it's linked hash set. And for linked hash set, did you see London is the first insert, so it keeps, is it? And then Paris, so it keeps the order of the insertion order. So that's what's the difference between linked hash set and just the general hash set, okay? So when you choose which set you want to use, so it's based on your application, okay? What kind of feature or property you want to keep. Okay, that's regarding, let's go back to the slides. The linked hash set, we are done also, hash set, linked hash set. And then next, let's see what's next. Okay, then the next one is regarding sorted set and tree set, is it? And sorted set, remember, it's still interface. Okay, so it says it guarantees the elements in the set are sorted, okay? And the tree set, it's a concrete class, okay, concrete class. And let's say we can still using iterator to traverse, okay? And it says elements can be sorted in 2 ways, okay? So let's see what that means. What are the 2 ways for the sorted? It says one approach to sort is you use a comparable interface. So we already learned that, is it? And the other way we know for comparing, is it? Comparing in Java, there are 2 approaches you can do comparing. One is comparable interface, is it? The other one is what? Comparator interface. Okay, comparator interface. And we also know comparator interface is very flexible, okay? And a lot of collection, the method when they take a comparator interface, is it? So here, what it means for the sorting, you can specify the way for comparing. One is using comparator interface. Then in that case, that class itself, is it the object needed to implement that comparable interface? Is it? But for comparator, you can, itself can be independent. Is it? You can define some class that implement whatever the approach you want the comparator to do the implementation, etc. So so that's the 2 approach for the comparing, okay? And here that's the, generally speaking, for comparator is what? Is if your class doesn't implement a comparable interface, is it? And you don't want to use a compare to method that's defined in comparator, is it? Then you can define your own comparator class, is it? And then you call it. Okay, so it allows both approach for comparing. And here, this example is going to use a tree set, okay, tree set. And it's still for string, okay, for string. And here it says the string going to be sorted using compare to method in the comparable interface, okay. And here it also says the example also creates a set of geometry object. And this geometry object, then they are going to use that compare method in the comparable interface. Okay, so let's see this example. Then I need to go back to that example. Okay, so let's take a look at this example. Okay, here. Do we have, there is no geometric. Maybe the other one. Okay, so first let's take a look at this example anyway. So over here first, this part we already know, it's that hash set we created, is it? And we create this tree set with the hash set. Okay, so this is also fine. Then you just output the tree set. Okay, so tree set internally also has a toString. That's what over here you can directly use the print. And then because the tree set is sub-interface of sorted set and the navigable set, is it? So you can call the corresponding method in both interface, is it? So for sorted set, you can have first and last, and the head set and tail set, is it? And for navigable, then you can have lower, higher, is it? And the floor, ceiling, and the pole first and pole last, and then you can also do the output, is it? And also here, be careful, is for lower, higher, floor, and ceiling. You see, you don't need to specify the complete the item. So the item within the set, is it? Because this is an item not in the set. You can also do that. That's also allowed. So then it's just based on the comparison. Okay. Then pick the item or the set of item using this item for comparison. Okay. Okay. So this is, we can take a look at the running result. Okay. Let's see directly. Yeah. So this time, if you take a look, the running result is that it's a tree set. So it's arranged in ascending order. So by default, okay. And you can also call like the set the ascending order not true, call reverse. Is it? Then it can do the descending order. Is it? And it will give you first to last. Is it? And head set. Is it? Head set here is specifying New York. Is it? So it will take. So it's a head set. So all of the items before it. So that's what a head set returns. And you can also see then what's next is a tail set is for New York. Then this time New York itself is included. Is it? So starting from New York all the way to the end. Is it? And then also find some item. Is it? So here it's lower. Is it regarding P, capital P, and regarding capital P? Is it? And what we have is we have London and then New York, is it? And then here is Paris. Paris, is it? And you are looking for the capital P, is it? So capital P is between New York and Paris, is it? So that's why the lower will give you the one that's next to P, but on the left, is it? And the higher will give the one that's next to it on the right. That's why it's New York. And the ceiling will give you the Paris. And the floor will also give you New York. So it will just return the item and the pole first, the pole last. And the pole first, pole last, remember, okay, it returns the item and also removes, okay, removes it. Okay, so be careful. So that's why you can also return the item and you can see the items are removed. Okay. Okay, so that's regarding the tree set. I just need to close this window. And then let's go back to the major information. So tree set we are done. And what next? Okay, the next example, and I believe, yeah, over here, is a test tree set with comparator. Okay, so let's take a look at this example. This example, I needed to share this, share that example. The previous one, if you recall the string, the tree set with the string, is it? And in that case, so string class itself implements a comparable interface. Interface, is it? And so interface, then internally it calls the compare to method. Compare to method, is it? And this time, let's see. This time we create geometric object. Okay, geometric object for the tree set. And over here, when you initiate the tree set, what you said is that I'm going to use a specific comparator. That comparator is defined by the geometric object comparator class. Okay, so basically that class implements the comparator interface. Okay, and it's I believe it's back in some previous chapters about this comparator, this geometric object comparator class. Okay, and then because you define this tree set is going to be when you do the comparison is going to be based on this comparator, this specific comparator class, is it? And then in this case, did you see you can add a rectangle, add a circle, so they are different shape, is it? These are the different shape, but you can still add off them into this tree set. And it's because the comparator class use whatever, maybe area or maybe a circumstance, is it, to define the comparison. Okay, then it's added to this tree set. And then go ahead, what's next does it's also use the iteration to do the loop, okay, for each loop. And we can take a look at the running result, okay. And let's see the running result, what it gives us. The running result, let's see how many we have. We have 4 geometric object created, that we have 4. And but when we do the loop, did you see the loop? You only have 3 objects. So here we have 4 objects added. But over here you only have 3 objects, geometric object. And looks like the comparator is based on geometric objects area, is it? Area, if you see the running result, is it? And why? It's because these 2, if you take a close look, they are the same, those 2, not the same object, is it? So we have 2 circles here. but both of them have the same radius. Is it? And if they are the same radius, is it? And they consider the same one. Yeah, it's because the dot equals method, whatever defined in the geometric object. Is it? So it consider the same one. That's why, and also over here, it's arranged as a tree set. Is it? As a tree set. And in ascending order here. Ascending order, it's by, so based on the output, it's by the area. Okay, the area. And over here, why only one circle? Is that because the definition of the equals, is it? So then only one circle is added, even though you have two circles object, but those two circles consider the same, is it? Because both at the same, they have the same center, is it, and the same radius. So they are considered the same geometric object. So that's why when you add to the set, they only consider a single object, okay? So be careful here. So what this example try to show is when you have tree set object created, okay, you can also use comparator, whatever the comparison you want to specify to create that tree set, okay. So that's this example try to show. And then next, let me close this, go back to the slides to see what more we have, okay. And this is regarding the tree set with different comparison, performance of the set and list. And for this example, after class, I recommend you can go ahead to check. So it's compare the performance of like array list, linked list, and the set. Okay, so you can take a look. If, and next, let's take a look another example, okay, regarding the application of the set concept. And this, I think it's more helpful. Oh, I needed to go back to share the code. Okay, so this time, let's take a look. Take a look at what this example does, okay? So anyway, so this example, it does count keywords. Okay, count keywords. So it's going to have some file, okay, some file. And then it count, it call this count keywords. Okay, so let's take a look at what that count keywords does. So the count keywords over here, it has an array of string. It lists all of the keywords, okay, keywords. And what next it does is, so we have this variable called keyword. The type is some set, and it's a string type of set, okay? And this, we use a hash set, okay, hash set. And then we plug in this of the keyword array, okay, we plug it in. And what the next one try to do is, so this set, it has unique keyword, is it? And what next is you just get some random file. So a file, you read in a file, is it? And with the file, you're going to read the file word by word. Is it word by word? And for every word, then you are going to see if that word is in that key set. Is it? So that's over here you call the contains. So basically over here it involves lookup. Is it? Lookup. And if it does, then you use a counter to count how many keywords in your file. Is it? So that's, so how many keywords in the provided file. So that's what this example does. Is it? So some similar application, you see, you can kind of borrow this concept. Is it? So we can take a look. Okay, so what this example does, it has some file, okay, called welcome.java, and it said the number of keywords just 5 keyword. Is it 5 keyword? Okay, so here it shows one of the application, okay, about set. So how do we use set? Okay, and then next, let's see. Okay, so this is a set application. And next it's map, as yesterday we discussed. So just be careful, okay? Map is not in the collection hierarchy, it's itself, okay? And also map involves a key value pair, okay? So it has a key part, has value part. And in Java, both together consider as an entry, okay, as an entry. So just keep this in mind. So this is regarding map, and then the map hierarchy is it's pretty similar arranged as set. You have sorted map, navigable map, it's pretty similar. Then you have tree map, is it? And we also have tree hash map and linked hash map, is it? And yesterday we also discussed the key idea about a map is key value pair, is it? And the key value pair, the purpose for map is it's very efficient in looking up, is it? With key. Because you don't need to do one by one comparison, is it? You just look for key, is it? And if you implement it with a hash set, it's what? It's order of 1 for the time complexity, is it? So map is used a lot if you have a lot of like lookup and you arrange your data structure as a key value pair. So map is quite used quite often. Okay, so this is regarding general map concept. Okay, and for map, so the contains key, is it? So that's a quick lookup, is it? And it also has the contain value, is it? And the entry set, so this will return the set of the entry, is it? You can also get the value with specified key, is it? So this is quick lookup, is it? And you can also get all of the key and all of the values, is it? So this return a set and return a collection, is it? And it also allow you to add a new key value pair, is it? You can also remove an existing key, is it? So this is a general map interface. And the hierarchy, is it? And it's pretty similar as set, a lot of methods for sorted map and navigable map, is it pretty similar? And yesterday we also said for the linked hash map, so the difference between linked hash map and the hash map is keep order. Is it keep? It's not just insertion order, okay? Or we call it the order of its least recently accessed. As access, least recent as you move it, the least recently accessed is at the beginning. At the beginning, is it? And the most recently accessed is at the back, because it's linked implementation, okay? And the other concepts are similar, okay? Floor, ceiling, walls. So this is, and also this entry concept, okay? So always keep this in mind, okay? So if you want to get all of the items within a map, you can have the entries, okay? It's a set of entries, okay? And hash map, tree map, and I remember we already discussed, is linked, we also discussed. So let's take a look the textbook example, okay? Let's first, let's go back to the share. Okay, so here we have the hash map, okay? So first we use a hash map, and this hash map, the key is string, and the value is integer. Okay, value is integer. And then did you see, then you can add the key value pair that you just put. And we can display all of the entries. Is it? And the second part is using a tree map. Is it a tree map? And this tree map is arranged with what? Using the ascending order of key. And the key is string, is it? So it's going to use strings lexicography order, is it? So that's what this one shows. And then next, let's take a look. The third part, create a linked hash map. And here, if you recall, if you initiate like this, then this first is the capacity. That's the initial capacity, okay? The second one is called load factor. Load factor. So the initial internally, when it implements, okay, it will just kind of use an array size of 16. Okay, and later on, if you want to add more items, so if your map size reaches 16 times 0.75, it reaches this size, then the capacity will be increased. I don't remember exactly, maybe doubled or something, or tripled something. Okay, and over here, because it's using hashing, later on we will also see when we learn the hash code hashing part, then it involves rehashing. Because if you use original, it won't work. Okay, so that's about the initial capacity and the load factor, okay? And anyway, so here it involves keep
A question.
insertion. Yeah, please.
So it has 0.75 F, and then after comma it says true. What does that mean?
Oh, that one, that's a very good question. That true, yeah, I haven't, we can, hold on, okay, let's, I kind of forgot about it. Yeah, that's a very good question. We can go to, hold on, okay, let me get to Java 8. This is linked hash map. Okay. Let's bring that document and we can sharing screen. Linked hash map, is it the official document? Let's see. Linked hash map. Oh, it's okay. Very good question. Okay, it's defined here now. This one, the third is regarding that access order. Yeah, so we set it as true. Is it? We set as true. That's why. So in this case, it's just not just the insertion order. So it's based on the least access, least access. Not least recently access and most recently access. So if you set this as true, okay, then it will also keep your access recent or least recent. So it will arrange it also as this order. And because for your insertion, is it for the initial insertion, then definitely it will keep this access order. But later on you may use some items in the map. Is it in the map? Then they will be rearranged, the order. The order will be rearranged by this least recently accessed or most recently accessed. Okay, so that's what this third argument is meaning, okay. And then let's get back to, I need to bring that example. Okay, and start sharing. Okay, and then let's see, yeah, over here. Over here, you see, initially, is it, so initially we have this insertion order, is it? And then did you see you access Louis, is it? Access. So this is going to be most recently accessed. Is it accessed? So it will be moved to the it will be moved to the beginning. Okay, it will be moved to the end. Okay, so least recently accessed at the beginning, most recently it will be moved to the end. Okay, and we will check. Okay, and then over here, the last part is just that for each, you can then output the name and the age. Okay. Okay, so that's regarding this example. And
the last question.
Oh, okay, please hold on.
s-
I can run this. Yes, please. With this code.
So when you insert an item, where does it go? In the end, since it least accessed? How does that work?
When you do the insert, it's arranged as the least one. So least one is the first inserted, is it? And if you insert last, so here is Cook, is it? So here the first is Smith. You first insert Smith and you last insert Cook. So this is most recent access. Is it? Okay, and then we can take a look at the running result. Okay, let's see the running result. How did I bring this running result? Let's see. Let's take a look at this part. The first is this is a hash one. It's a hash one, so not order. So first, let's take a look. This one, the hashed one. How do I bring this? Hold on, okay. Let me figure out a way to, so that you can see the, maybe I need to.
I think you used answer.
Yes, but how can I let you all see the answer?
There's a scroll bar on the right. You could move it.
Hold on, but the problem is I want, okay, now this should be fine. I don't want it to be, let me see if you can see the running. Okay, I can scroll, you're right, yes. Let me then share this one. Okay, and the first one is a hash one. Is it? The hash one, Smith is first. Cook is last. But if you see the running result, definitely they are not as your insertion order. Is it? Okay, and then the next one is the tree set. Is it? And the tree set is based on the key. Is it a key? So should Anderson be first? Okay, let's see. The tree set, why it's okay. If you take a look, it does arrange in ascending order. So Anderson is first, Smith is last. So this works. Okay, and then the third one is the linked hash map. And we set this access mode as true. Is it as true? Did it? Let's go. Okay, let's see. Okay, the linked one, did you see Smith is first? Smith is first. Anderson is second. Anderson is second. And then Louis, supposed to be Louis, is it? But if you take a look over here, it says display. Is it display the entries? Supposed to be Louis, but what it does is Cook. Is it? Why? Because over here, you retrieve, you access Louis again. So that's why Louis is moved to the back. Is it? So this is most recent, mostly recent access. Then it's moved to the back. Is it moved to the back? So that's how this linked hash map be arranged. Okay, and but be careful. Okay, for linked hash map, if you do lookup, okay, if you do look, it's just generally speaking. Okay, the time complexity is still order of 1, but later on we will see. With the hashing, it's not strictly in this case. Okay, it's not strictly this case. So it's just generally speaking, it's an order of 1. Okay, constant time. And for the worst case, worst case regarding hash map, it can still be order of n. Okay, order of n, because later, and you can also kind of, if you recall that linked list hash table lab that you did, hash table, that hash table example, and you have a bunch of linked list, is it? And this is sub 0, sub 1, is it? And it's purely based on the hash. And if all your all entries hashing result is 0, then all your entry will be added in this linked list. Is it in this cluster? Will all be crowded in this single cluster. And in this single cluster, then it's still order of n. And that's why we say this is worst case. Okay, with worst case, with a hash. So even though map has, generally speaking, has the advantage of constant time lookup, is it? But it depends on how you arrange the hashing. Okay. Okay, so anyway, so that's later on we will also discuss the hashing in more detail. Okay, that's regarding this tree map. And let's move on to the next one. And oh, the last one. I think we are going to go to the last example. Okay, count occurrence of words. Yeah, this is a very pretty common whenever you learn map example application. Okay. Did you see my example, or it's still the slides?
Still slides.
Oh, still slide. Okay, let's go back to the example. Okay, and this is also a classic map usage. Okay, and for this one, so you have a string, maybe it's a book. Okay, something like that, is it? And here we create a map as a tree map. Okay, tree map, and the key is string, and the value is a number. So basically what this example try to do is it will have some word and the number of times that word occurred. Okay, maybe in a book or something. Is it in a book? And this is a classical example, okay? And basically this is also like if you learn like a parallel processing, etc. This is also a very classical example. And anyway, so here with regarding this specific string, we are going to extract every single word out. So this is regex, okay, regular expression, and you use some space, etc. And here is punctuation, so anyway, so punctuation, okay, so like exclamation mark, like those called punctuation. So you're going to use those for the token, as your token, is it? And then you're going to convert of the word to lowercase, okay, to lowercase. And so we store them in an array, okay, store them in an array. And then what you are going to do is you are going to have a map. Is it here? We have this map created. So we are going to add each of the keyword. Is it? Add it to the map. So you call put, add the key. And because this is the first time it appears, is it? So that's why the occurrence is going to be 1 if it's not in the key. is it? Otherwise, if it the key is already, the keyword is already, the word is already in the map, then you're going to count. Is it? You're going to count it, increment it, and then you update. Is it? So here you update value. Okay, you update value. And there is some other way you can write. Okay, I remember you can do like put as default or something. Then in that case, you don't need to write if else. Okay, you can just do put as default, then specify this one as a default. If the key not exist, it will take the default value. Otherwise, it will increment and add with the new value. So you can also write in the other way. Okay. So anyway, so then in this case, you are going to fill the map, is it, with all of the key and the word and the number of times it appears. Okay. Okay, and then let's take a look at the running result of this example. Okay, so if you take a look at the running result, as it does give you each word, how many times it appears, is it, in this string. Okay, and this also can be applied like to a book. Okay, and okay, and I think we let's see the slides. If we, yeah, basically that's all of this chapter's material. Okay, so we are done with the learning of set and map. And so starting next week, we will move on to a balanced binary tree. Okay, so how there are some approaches, because so far what we learned is just the binary tree, but it's not balanced. Okay, but a lot of time you see when we consider the time complexity, it's that like the tree map, as we said, if it's a tree map is arranged as balanced binary tree, is it? So how do we balance that? So next week we will learn AVL tree. Okay, so that's all for today. Are there any questions before we